This is a talk we added in, as Joe just said, but sort of following the nuts and bolts idea behind this conference. I wanted to show you a problem that we worked on very early on in our planning for persistent memory. It's not as maybe sexy as a lot of the other talks because they're kind of cutting edge. How do we solve this new way of using persistent memory? This is more about how to solve the old ways of using storage with persistent memory. And but we had to take it seriously in order to get adoption of persistent memory to work. And so we came up with this programming model. But even before this programming model, most of the talks, well, probably all of the talks, but this one, are over here on the right-hand side of the programming model where applications are modified to map and use persistent memory. But what about this middle part here, these legacy storage APIs? I think we really have to take seriously this idea that unmodified applications and unmodified file systems also need to work on persistent memory, if only to help the ecosystem transition. So we decided very early on this was very important. Just run it in a virtual machine, and actually the problem I'm going to describe here even applies in this case. So thank you very much. That's a good straight man comment. And so, how hard could this be really? I'm really just talking about the idea that at some point, applications or file systems are just expecting a block interface, right? The operations are block read, block write, very simple. Since we're writing a new driver for persistent memory in all of the major OSs, we can handle it there. And it's, like I say, probably not so hard. You just take the block address that you're passed and you figure out, well, persistent memory is just this big array of bytes. So I just take the block size that I'm pretending I have, I multiply that times the block number, and then I just do a mem copy there. Done. Any questions? Okay, we're finished. Except for what happens now when failures happen, right? This is where it always gets interesting. So on a read, I don't think there's anything too amazing here. If I imagine doing a read from a traditional storage device and I lose power, I don't think any software would be surprised that the DMA maybe got partially through the read and then stopped. Okay, well that's of course what's going to happen here. The mem copy is going to get partially through the read and then stop. So okay, I think everything's okay. What about on the write? Well, on the write, let's take a look at what happens when on traditional storage when in-flight writes are interrupted by a power failure. So here's my traditional storage picture. What I mean by in-flight writes are writes where you've submitted them down to the storage device, but you haven't yet heard that the write is complete. So those writes are in flight. And typically these storage devices have some sort of a queue depth, the number of operations they're willing to have going concurrently. And so just assume that there's one or more of these things that are going. So this is actually it seems like it's kind of straightforward, but if I at the time I kind of went around and looked to see how these were handled by different devices, and I started with hard drives. So if you give a hard drive a very large write, let's say you tell it in one command to write a megabyte, nobody is surprised if a power failure interrupts that megabyte and only some of it got written. That's fine. Where the surprise comes in is what happens to an individual sector that was being written at the time of the power failure. Now, the very first thing I did about 7-8 years ago is I Googled this, and I found very authoritative people telling me that these can never be torn, that these sector writes are atomic. And in fact, these very authoritative people said, yeah, the rotational inertia going in the drive is used as a source of energy to complete the write. And I'm like, oh, wow, that's really cool, right? So of course I went and asked manufacturers, and I kind of got answers back from, yeah, well, I'm sure we do that, to answers like, sure, I guess somebody could do that. I didn't feel very comfortable about it. Well, of course, it also turns out that I was at Sun when we started the ZFS project, and as soon as we added checksums to blocks on the file system and we started testing different drives, we found interrupted torn writes all the time, right? So they can happen. They're not guaranteed by a spec, right? The SCSI spec or the ATA drive spec is silent on this matter. It does not guarantee that these sectors are atomic, Powerfail atomic. In fact, they're usually not even guaranteed by a manufacturer. I honestly could not get a manufacturer to tell me that that torn writes were impossible. I certainly got lots of best effort kind of language, right? Yeah, we'll do our best, to not tear it. But this isn't as bad as it sounds, right? Because these drives have metadata that they store along with the sectors. So a sector can be torn, but they try and make it as rare as possible in the design of their drive and the design of their firmware. And they typically have some sort of error correction code around the sector. And so what happens if you interrupt a torn write, if you interrupt a write and you get a torn write, on recovery, either you get the old sector or you get the new sector or you get an error because it got interrupted. So really that's not bad, right? If you imagine, okay, a little inconvenient that the write got interrupted, but I got an error, so it's not silent data corruption, right? Not a problem. In fact, I would say, and this is maybe me going out on a limb a little bit, but if you found a case where a drive gave you some old data and some new data and no error, and you went to a manufacturer, I would say they're likely to consider that a bug and to try and eliminate that case. Like I said, we did find some of these cases on some drives, especially and it's very hard to catch them do it. It really is. It takes a lot of test framework, which we learned the hard way in the file system group. But like I say, it's much more likely that you get either old data, new data, or an error. So it's really not that bad. These are rare to begin with, and getting an error is okay, right? It's the silent thing. So what about those? So those are hard drives. So what about SSDs? Well, the slide for SSDs is identical, only I add one little thing here. For an SSD, it turns out that, again, SCSI, ATA SSDs were around for a long time. There was no guarantee. But in NVM Express, when the committee was coming up with the definition of NVM Express, some bright people on the committee decided, that this was back when it was called ENVM HCI, if any of you were on that committee, they decided, a lot of people really want this Powerfail write atomicity, so let's have the drive tell you what the Powerfail write atomicity is. When you do an identify drive on NVMe, you get back a number, and the smallest value you can put in that field is 1. Right? So they require, you cannot be an NVMe drive unless you have at least single sector Powerfail write atomicity. I think it's awesome. I wish all drives did this. So that's great. So again, now you at least have something that you can depend on. Okay. Now let's talk about my little memcopy driver in persistent memory. So a memcopy is just a loop of loads and stores. So between any two store instructions, if you interrupt the memcopy, if you have a power failure, the ECC in the persistent memory is correct, right? So, there's no way to tell that the sector was torn if it's just a memcopy. The sector will contain some of the old data, some of the new data, and no read error. This is the common case for persistent memory, right? We've taken something that I argued was extremely rare and at least had an error indication, and now we've made this horrible thing that even people we think would say it's a bug. We've made it the most likely thing to have happen, right? If you've got writes in flight and you interrupt the system, in fact, it'd be pretty unlikely, but the rare case is now that you have no torn sectors, right? Because you'd have to catch it right in between the memcopies of multiple sectors on a busy system. Okay, now I just want to reiterate, no spec ever promised that there wouldn't be torn sectors, right? And you heard in Dan's talk this morning how a lot of people get this wrong, but the user data, the current state of user data, unless you've heard back directly that your sync has completed, it's on you, right? It's on the application. So nobody was promising this. But the problem is that these were rare in the past, and now they're really the common case. And they're so rare in the past that buggy software that depends on this has existed for decades. It's really been out there forever. And no one's ever done anything about it because it's rare. So no problem, why don't I just go fix all the buggy software, right? So I started looking at who depends on these atomic sector writes. Well, a bunch of file systems do, including the single most commonly used file system in the world, NTFS, right? Depends on this. It's like, okay, well, I can work with Microsoft to fix NTFS, but there's a zillion machines out there already running NTFS that doesn't have the fix. But we found it in ext4 and XFS also, by the way. Lots of these file systems had this problem. And lots of applications. I mean, they're just all over the place. The assumption that these sectors are atomic is all over. The Win32 API, if you go look it up on MSDN, says that sector writes are atomic. Right? The API is documented that way. POSIX doesn't say that. POSIX never promised it. So, that's where you get the, oh, well, it's your problem, kind of response. But of course, that's not really what's going to happen. I'm trying to introduce this new technology into the ecosystem. If people are getting silent data corruption, they don't want to lecture on POSIX, right? They want it to work. So I'm convinced that I have to fix this, right? And this is, like I said, this is very early on. This was before our first SNIA meeting. This was before we first even came up with the programming model. I knew that if I wanted any sort of legacy usage of persistent memory, I had to fix this. Okay, so how do I fix this? This is, we're all still learning how to do persistent memory programming. How hard could this be, right? The first idea I came up with was, well, this is no problem at all. I just add a little checksum after each write, just like a drive does, right? So now, if the write of the block gets interrupted, later on when somebody tries to read it, the checksum won't add up, and you're not told. So I got rid of the silent data corruption. But again, remember, because the ECC is correct between any two instructions, and you can interrupt a mem copy with a power failure, then virtually all writes that were in flight will now be in this state where they return an error. So goody for me, I got rid of silent data corruption, but does that really matter when all the blocks return errors now after a crash? No one's going to be happy with that. So I wasn't really happy with this idea, and actually I just put it on this slide here more to explain it, not because I ever seriously considered implementing this. But this kind of atomically updating a block is very common in databases and other kinds of applications. And the most common way of doing this is write-ahead logging. So why don't I just do that? So I write the block first to a log, like this. Then I actually update the block in place. And in recovery, I look to see if there are any log entries that where I didn't get finished logging the block, so those can be discarded. And I look to see if there are any where the copy into the final resting place got interrupted, and I can finish those. So it's very simple. This would work. Like I say, it is actually pretty common for databases to do this, but it has a write amplification of 2, right? So now I'm in this space where I've got persistent memory. Yes?
Question.
Yeah.
That second write isn't one for one, right? Once you write the log, everything gets written in the log. But that checkpoint 5-minute rule takes a while.
Yeah. So I wouldn't acknowledge the write, though, until they were both done. So I would do it immediately, is what I'm talking about.
If you had 2 logs, you could acknowledge the write, because the log is the database in that case, not the incorrect data store.
Yes, I think I understand what you're saying, but my point is really that however you lay this out, yes, you're still writing each byte of the data twice, plus some metadata.
It's true, but they're concurrently written. It doesn't take any more time.
Doesn't take any more time. So I think it's important to realize that these things are DIMMs, right? There's no DMA engine. So every byte that I'm talking about is being copied by the CPU, and nothing else is happening in that thread until it's done. And the amount of time it takes you to context switch to a DMA engine or to another thread is far greater than the amount of time it takes you just to copy the data. So this does kind of go to my bottom line of performance.
On the memory channel, which we're sort of going towards,
these stores are sort of zero time, because the way that old memory worked was you would find out that the failure of that store in a machine check. And so it's like the only thing that's going to make that thing work is erasure code, right? So it's not, you're not really waiting for those IOs.
So they are posted, but they have to be, I'm trying to maintain the semantics. This is a really important question. I'm trying to maintain the semantics of when an application knows that something's persistent, right? And on a hard drive, the application knows, or at least believes, that something is persistent, right, once the block has been transferred down to the drive. And so I'm trying to get those semantics here, which means it's not just the posted stores have to be completed, the cache flushes do too.
Those semantics are kind of dinosaur semantics. You're probably going to go the way of the dodo, because...
Right, but they haven't yet, and I'm talking about the legacy path. But I'm talking about the legacy path, so I'm talking about existing software, trying to make sure that that works correctly. So that hasn't gone the way to dinosaur yet. I want it to. I'm with you on that, but it hasn't yet, right? So, yeah.
And why were you concerned about every write in flight getting an error when you restart. Is it because almost all of those writes did not depend on not tearing the sector? So
Right.
is that it?
Indeed, it's that the behavior that these applications were used to was that they wouldn't get these torn sectors. They were actually depending on it. To give you an example, a database keeps a log and knows that he can append these 512 byte sectors because it's old from the SCSI world, right? And these sectors, the existence of the sector at the end of the log is what it uses to decide whether that log entry is complete or not. It doesn't checksum them, right? Now, a lot of databases do checksum, and that's, of course, not my problem. Then everything's fine. But the databases that don't checksum them, they're wrong. They should be checksumming them, but they're not. And I want them to continue to work the way that they believe they've been working all these decades. So, if you go look at RocksDB and you look at the little 512 byte thing that RocksDB appends, there's a CRC at the end of it. It's beautiful. Nobody worries about torn blocks with RocksDB. But I found plenty of databases where that wasn't the case. So just to keep this moving, so my write amp of 2 here is what I'd like to get rid of. This stuff is fast. It's a lot faster than storage. So just the fact that I'm copying every block twice is actually pretty annoying performance-wise. So what about a better approach? Well, like I say, yeah. It's still quite a bit faster. I'll give you that. Yeah, I'd say it's like somebody gave you $10 and gave you back $5, but I want it just to be $1. So we can do better, right? And so like I say, I was at Sun when we started the ZFS project, and we decided on a big rule about not writing anything that's in use, right? Every write is an allocating write. And I thought, well, I could just do the same thing here. Every write can be an allocating write. I write it to a new location, and then I just have to update a little bit of metadata that says that it's there. And not to keep you in suspense, what this means is that every read requires consulting a little map. Our map turns out to be an additional one load of a 32-bit value. So it's not so bad, especially when you get up into these 4K blocks. It gets amortized pretty well. So for every 4K block you read an extra 32 bits. It's not bad. On the right side, every time you write a block, I've got 1 read and then 2 stores, plus the cache flushes to make things persistent. But again, the larger the block, the more amortized this is. So this is the thing I set out to implement. And so like everything in programming, I solved it by adding a level of indirection, which I call the map. And the map shows the current location of any block. At any given time, block 5, you find by going into the map at location 5 and find its actual address on the persistent media. You get back, I call it an internal LBA number instead of the external LBA number that was passed into the driver. This gave me a little opportunity in the map to add a couple of bits of metadata. I added a 0 bit and an error bit so that if a block was believed to be 0, for example, if the driver received a trim command for that block, then you only have to read the map to find out that the contents are 0. When somebody accesses that, you say, oh, the 0 bit's set, and you just return back a block of zeros. Same for an error. There's an operation that a lot of people don't even realize exists that scores a block on a drive so that to force it to return an error. It's used by RAID stacks to make sure that a stripe will always return an error until it's fixed. So anyway, I implemented those 2 things. I want the updates to the map to be atomic. So on x86, store to persistent memory is Powerfail Atomic if it's 8 bytes or smaller. Thank you. And so these turn out to be 4 bytes. And the reason they're only 4 bytes, because these things can be many terabytes in size, is because we use this thing called arenas, where we actually take a really big namespace and we break it up into arenas. So the map is a map just for the arena, and each arena is about half a terabyte in size. So you kind of just replicate this idea a few times. So how do I make this work? Well, I need to manage a free list. I need to manage a little list of where my blocks are for doing writes. I combined this free list into kind of a log of an atomic operation, so I called it a flog. And the flog is just this little data structure there that has to have 1 free block in it. It has to refer to 1 free block. It's a very tiny data structure. It just tells you where the free blocks are. And it has to refer to 1 free block for every possible write that could be in flight. Well, our queue depth for persistent memory is just the number of hardware threads, right? That's how many writes you could have going. So it's essentially NCPU. Okay, and I'm going to show you probably the most interesting part of the whole thing was how we decided to do these flog entries atomically. So I came up with this idea early on. I called it Schrodinger's pointers. These are pointers that kind of exist in two states at once until you actually try and use the pointer, and then the wave packet collapses, the cat is either alive or dead, and the pointer points to one place. So this is a flog entry, and it has a shadow version of the flog entry. Inside each flog entry is the block number, the contents that is trying to be changed in the map, and a little sequence number. And you just ping pong back and forth between these two things. Every time you update it, you write the one that's not in use, you write to it, and you write its sequence number. And the sequence number of the version that is currently correct is the higher sequence number on this circle, right? Because there's only 2 entries and there's 3 possible sequence numbers on this circle. So one of them is always going to be to the right of the other one. Okay, so you can always tell which one is the valid sequence number. And so if I write code to go ahead and update this flog, I'm going to update the first 3 values. I'm going to make it persistent. And then I'm going to update the sequence number and make it persistent. Piece of cake, right? But there's 2 flushes here, and again, I'm trying to make this as fast as possible, and the flushes really piss me off. So, instead of taking this 3 value write and then a flush, and then the last value write and then a flush, this is one of the most important lessons we learned, and this is used all over in a bunch of persistent memory software that's been written by these companies, a lot of these companies since then. We take advantage of a property on x86 that says a younger store won't pass an older store if it's to the same cache line, right? So in other words, I cache line align these, and now I can write all 3 of these. I still haven't flushed anything. I can write these in any order, but I write the sequence number last, and I do a flush, and now it's all just one flush. In fact, of course, I think a lot of you are there already, we can use these non-temporal store instructions that go around the cache, and this is actually quite fast.
Isn't there a limit on that thing with x86?
It has to be in the same cache line, so 64 within the same 64 bytes.
How many such entries will it keep in flight?
I mean, this is just a property of how the cache hierarchy works inside of x86. It could be thousands, right? Yeah, because I mean, just think about it. It's basically saying that there's kind of 2 situations here. One is these things got evicted from the cache earlier, but in which case they're there already. But there's no way that this will get evicted from the cache without taking these along with it, right? And that's true for both cache, normal stores, but also non-temporal stores, which are in a store buffer, like you say.
So you have to affinize very carefully, and you don't allow cross-processor access.
Right. So in other words, your thread is currently updating this one entry.
Yeah, but it can't get context switched.
The context switch is a serializing event, so it would still work. Serializing event, at most, could flush these things out. So it does work. And it's in the SDM. It's documented even. Yeah?
Don't you need any fences between those stores?
You don't. Not if they're in the same cache line. I just have to emphasize this. Don't do this if these things cross cache line boundaries. Then you do need fences.
So isn't the processor free to reorder stores based on like the performance characteristics, as long as they don't basically touch the same data?
So,
They're not touching the same data, but they're in the same cache line, so the processor can just reorder them, and nothing is wrong with doing that, right?
Right, the compiler is free to do that, and will do that, and you have to keep it from doing that. But like I say, these can go in any order. You just have to make sure this one's last, and you can do that easily with a compiler directive, which is what we use to make sure. Actually, if you just mark these things as volatile, they won't get reordered, right? So, like I say, it's kind of a simple thing, but 64 bytes is actually not a bad amount of data to keep. You can see I can keep at least 4 fields. These are only 32 bits each, so I could do a lot more. We ended up using these kinds of little 64-byte things as little tiny redo logs all throughout PMDK. And this little trick here saves you. Every one of those flushes is important, right? Every single one of those is what we spend a lot of our time removing. So just to keep this moving here. So finally, I kind of went through this already, but the whole read path now on this code is that you fetch something from the map, you look to see if you already know what the answer is by looking at those 0 or error bits. Otherwise, you fetch something from the data area, check for errors. Somebody already mentioned machine checks and things like that. Those checks do still have to happen. And then you can return the data or an error. On the write path, again, you're identifying the free flog entry. It's the flog entry assigned to you, right? Remember, there's as many flog entries as there are CPUs, so you know which CPU you are in the kernel. So you can just decide that this is the one for your CPU. You update the flog state first, and then you store it. And you can see at this point, then you've updated the flog, but you still have to go update the map. At the point where you finally write the flog entry with the new sequence number, this is the point of no return. So anything before here, the write will be undone if you lose power. Anything after here, the write will be completed, because on recovery, we'll see this flog entry and we'll see that it hasn't updated its map yet. So on recovery, we just walk through the flog, which is small, and just look for any map entries that haven't been updated. So adding this to the ecosystem, I first wrote, this is the first library in PMDK. I wrote it on an airplane. It's actually pretty simple. Well, okay, it was a flight from Poland, so it's 10 hours of work. But this code actually got used. My reference code ended up in multiple operating systems. They basically took what I did, and I had written it in a way where you could move it into the kernel pretty easily, and that's exactly what happened on some OSs. Other OSs implemented it from the spec, because I had written a spec. And we even did this great exercise of me writing a layout and giving it to them, and them writing the layout and giving it to me, and making sure that our implementations, and we shook out the bugs that way. It's pretty cool. Then we decided to standardize it. It's in UEFI. We put it in UEFI because that's a boot time standard, and you have to be able to boot from these devices. So it's in the spec. It's been a standard now for a couple years.
So that's boot, not reboot.
Boot, not reboot.
Boot is the first time the manufacturer brings up the system. Reboot is every other time you get.
Well, it's a boot device. You can reboot from it as many times as you like. That's why it's in UEFI. The performance is not terrible, but it's also not trivial. Even with all my careful coding and everything, depending on which OS it is, because some people have done more performance work than others. The write overhead, pure 100% writes, this adds about 15 to 20% overhead. So it's, like I say, of course, it soundly beats any storage device because it's persistent memory. But and it soundly beats the naive implementation of doing 2 copies with a write-ahead log. But I have to be honest. My first implementation of this was a hardware register where you could write a block, and then you set a little hardware bit, and it atomically guaranteed that the block was moved into the media. And it was on that register was on the first Apache Pass DIMMs that we had, but I lost it in a power budget fight because those little memory cells, those static SRAMs, they suck down a lot of memory. So I finally had to admit in a meeting that I wasn't proud of myself, where they said, "Couldn't software just do this?" And I'm like, "Of course we can just do that." And so then it was software's problem, and hardware was no longer going to do it. But it did raise aware of this write atomicity issue, and so now both ext4 and XFS have fixed this problem where they were dependent on the atomic blocks. It's only in certain configurations, so you have to be careful how you're configuring them, but they did fix it. Hopefully we'll see more of that go on. I actually think that eventually Microsoft will get tired of my BTT algorithm and they'll fix NTFS too. So that's it. I have time for a question.
I think one question, yes. I had my hand up. Going back to this issue of, you say you guys found that you can't trust media storage manufacturers, and other people.
Actually, they're within spec.
Ramsey says you can't trust them. Joe Tuchek at Labs said you couldn't trust them.
Yeah.
Right. So the question is, aren't you adding a layer of semantic sugar on top of unknown? And doesn't that mean that really you should be trusting on statistics and ratio coding and replication and doing something different than what you're doing, not waiting for a reply because you can't trust
So,
even if after the reply
okay.
is still there.
Okay, so here's my answer. What you're talking about is durability, and what I'm talking about is persistence, and there really are 2 different things. So I'm talking about assumptions that software has made about persistence that doesn't make something durable, and software is still responsible somewhere in the stack of making something durable by doing something like erasure coding or mirroring. If that all still happens here, on top of what I'm talking about. But I'm really talking about taking assumptions that were wrong, that everybody had about persistence, and going ahead and just implementing it anyway because it was easier to do that than to try and get them to be right. But I don't disagree with anything you said, except for I do differentiate between persistence and durability. So I think we have to call it because we're late.
All right, let's
So.
thank the speaker.